I want you to do something very simple. I want you to close your eyes. Take a slow, deep breath in. Hold it for just a moment. And now, let it go. Let your body sink a little deeper into wherever you are right now. Whether you are lying in your bed, resting on a couch, or curled up somewhere quiet, I want you to know that for the next long while, you do not need to be anywhere else. You do not need to do anything else. You do not need to think about tomorrow, or yesterday, or even 5 minutes from now. All you need to do is listen. Listen. And let your mind drift into one of the most beautiful and mysterious stories the universe has ever told. Imagine, if you will, that you are lying on a hilltop somewhere far from any city. There are no streetlights. There are no car headlights. There is no glow from buildings or signs or screens. There is only you, the grass beneath your back, and the sky above. And what a sky it is! Thousands upon thousands of stars are scattered across the darkness like tiny diamonds sewn into black velvet. You can see the faint, glowing band of the Milky Way stretching from one horizon to the other, a river of ancient light flowing across the heavens. You can see planets shining steadily among the twinkling stars. If you look carefully, you might even spot a satellite drifting silently across the sky, a tiny dot of reflected sunlight moving among the constellations. It is peaceful. It is vast. It is humbling. Now, here is where our story begins. Because everything you see up there, every single star, every planet, every moon, every galaxy, every nebula, every asteroid, every grain of cosmic dust, all of it, every bit of visible matter in the entire universe, makes up less than 5% of what is actually out there. Less than 5%. Let that sink in for a moment. If the universe were an ocean, everything you can see would be a few drops of water on the surface. The rest, the overwhelming, staggering majority of reality itself, is invisible. Hidden, dark, and the largest component of that invisible reality, the thing that holds galaxies together, that shaped the cosmic web of the universe, that made it possible for stars and planets and eventually life itself to exist, is something scientists call dark matter. Dark matter is not a poetic name. It is not a metaphor. It is a real, physical substance or collection of substances that makes up approximately 27% of the entire mass and energy content of the universe. It outweighs all the ordinary matter, all the atoms, all the stars, all the gas and dust, by a ratio of roughly 5-to-1. There is 5 times more dark matter in the universe than there is everything you have ever seen, touched, tasted, or measured with any instrument that detects light. And yet, despite being the dominant form of matter in the cosmos, we have never directly seen it. We have never held it. We have never captured a single particle of it in any laboratory on Earth, at least not with certainty. We know it is there because of what it does. We know it is there because without it, the universe as we know it simply cannot exist. Galaxies would fly apart. The cosmic web would unravel. Stars would never have formed, and you and I would not be here to wonder about any of it. So tonight, we are going to explore everything about dark matter. We are going to travel through nearly a century of scientific discovery, from the very first hints in the 1880s to the groundbreaking and controversial claims of 2025. We are going to meet the brilliant, often overlooked scientists who first suspected that the universe was hiding something enormous. We are going to examine every major piece of evidence, from spinning galaxies to colliding galaxy clusters to the ancient light of the cosmic microwave background. We are going to explore every candidate for what dark matter might be. From ghostly particles called WIMPs, to ultralight waves called axions, to tiny black holes that may have formed in the first fraction of a second after the Big Bang. We are going to visit the deepest underground laboratories on Earth, where scientists sit in silence, waiting for an invisible particle to nudge a single atom. We are going to look through the eyes of space telescopes that scan the sky for faint whispers of gamma rays that might, just might, be the signal of dark matter particles destroying each other in the heart of our galaxy. And we are going to do all of this slowly, gently, with the calm, unhurried pace of a story told beside a fire on a quiet night. Because this is not just a science video. This is a journey into the deepest mystery of existence, told in a way that is meant to help your mind relax, to let go of tension, and to drift peacefully into sleep. You do not need to memorize anything. You do not need to take notes. Just listen. Let the words wash over you like a gentle tide. And if you fall asleep before we reach the end, that is perfectly fine. The universe will still be here when you wake up, and so will its mysteries. Before we go any further, if this kind of calm, deep scientific exploration is something that helps you relax or learn, or simply find a moment of peace in a busy world, I would be grateful if you would consider subscribing to this channel. It helps us continue making these kinds of journeys for you. And if you have ever wondered about dark matter, if you have ever looked up at the night sky and felt that something vast and invisible was looking back, leave a comment below. Tell me what you think dark matter might be. I would love to hear your thoughts. Now, let us begin. To understand dark matter, we first need to understand what the universe is made of. And to understand that, we need to start with something very familiar. Look at your hand. If you can picture it in your mind, do so now. Your hand is made of atoms, billions upon billions of atoms. Those atoms are made of protons and neutrons, clustered together in a tiny nucleus, with electrons orbiting around them. The protons and neutrons are themselves made of even smaller particles called quarks, held together by the strong nuclear force. These atoms, this ordinary matter, is what makes up everything you interact with in your daily life. The chair you sit on, the food you eat, the air you breathe, the water you drink, your body, your brain, your bones, your blood. All of it is ordinary matter, made of the same fundamental particles that were forged in the hearts of ancient stars billions of years ago. Now, this ordinary matter is also what makes up the stars you see in the night sky. It makes up the planets in our solar system. It makes up the gas clouds and dust lanes that wind through galaxies. It makes up the hot, glowing plasma in the cores of galaxy clusters. Every telescope ever built, from the first simple refracting telescope that Galileo used to observe the moons of Jupiter, to the James Webb Space Telescope floating 1,000,000 miles from Earth, is designed to detect some form of light, some form of electromagnetic radiation, emitted, absorbed, or reflected by this ordinary matter. But here's the extraordinary part. All of this ordinary matter, accounts for only about 5% of the total mass and energy in the universe. That number comes from some of the most precise measurements in the history of science, taken by satellites like COBE, WMAP, and the European Space Agency's Planck spacecraft, which measured the faint afterglow of the Big Bang itself with stunning precision. When scientists analyzed the data, the numbers were clear and astonishing. The universe is approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. Let me say that again, because it deserves to be repeated. 95% of the universe is made of things we cannot see. 95%. We, with all our technology, all our telescopes, all our satellites, all our particle accelerators, are looking at a tiny sliver of reality. The rest is dark. Now, you might be wondering, what is the difference between dark matter and dark energy? This is a very important question, because even though they share the word dark in their names, they are entirely different phenomena. Dark matter is a form of matter. It has mass. It takes up space. It exerts gravitational pull on other things. It behaves, in many ways, like ordinary matter, except for one crucial difference: it does not interact with light or any other form of electromagnetic radiation. You cannot see it with any telescope, no matter how powerful, because it does not emit, absorb, or reflect photons. It is completely, utterly invisible to every instrument that relies on light. Dark energy, on the other hand, is not a form of matter at all. It is a mysterious property of space itself, a kind of anti-gravity that is causing the expansion of the universe to accelerate. While dark matter pulls things together, dark energy pushes things apart. While dark matter is concentrated around galaxies and galaxy clusters, dark energy is spread uniformly throughout all of space. They are opposite forces in a cosmic tug-of-war that has been playing out since the earliest moments of the universe. And right now, dark energy appears to be winning. The universe is expanding faster and faster, and the galaxies are drifting further and further apart with every passing moment. But tonight, our focus is on dark matter, the invisible substance that holds the cosmos together. The gravitational glue without which no galaxy, no star, no planet, and no living thing would exist. And to truly appreciate what dark matter is, and why scientists are so certain it is real, we need to travel back in time. Not to the Big Bang, not yet. We will get there. But first, we need to go to the late 1800s. To the very first moments when a few perceptive minds began to suspect that the universe contained far more than meets the eye. In 1884, one of the most famous scientists in the world, William Thomson, also known as Lord Kelvin, was giving a series of lectures in Baltimore, Maryland. Kelvin was a towering figure in physics. He had made fundamental contributions to thermodynamics, electromagnetism, and the understanding of heat. During these lectures, he discussed the speeds of stars near our sun, and tried to estimate how many stars would be needed to produce the gravitational effects he observed. His calculations led him to a remarkable conclusion. He wrote that many of the stars in our galaxy, perhaps even a great majority of them, might be what he called dark bodies, objects that exist and have mass and gravity, but do not emit any light that we can detect. This was, as far as we know, one of the very first suggestions in the history of science that the universe might contain significant amounts of invisible matter. A little over 2 decades later, in 1906, the great French mathematician and physicist Henri Poincaré was reviewing Kelvin's work. In his discussion, Poincaré used a specific phrase that would echo through the next century of physics. He wrote about matière obscure, which is French for dark matter. This is one of the earliest known uses of the actual term dark matter in a scientific context. Poincaré considered whether the amount of dark matter could be less than the amount of visible matter. As it turned out, he was wrong about that. There is far, far more dark matter than visible matter. But the seed had been planted. The idea that the universe might be hiding an enormous amount of invisible mass was now part of the scientific conversation, even if only at its very edges. In 1922, a Dutch astronomer named Jacobus Kapteyn took the next step. Kapteyn was studying the motions of stars in our galaxy, and found that their velocities suggested the presence of more mass than could be accounted for by the visible stars alone. He was one of the first to use the term dark matter in an astronomical context, and his work added another thread to the slowly growing tapestry of evidence. Then, in 1932, another Dutch astronomer, Jan Oort, the same Jan Oort who is famous for proposing the existence of the Oort cloud, a distant shell of icy objects surrounding our solar system, was studying the motions of stars in the plane of our galaxy. He found that the total mass in the galactic plane had to be greater than what could be accounted for by the stars and gas that were visible. Something unseen was contributing to the gravitational field. Oort's specific measurement was later found to be incorrect, but his intuition was right. There was more to the galaxy than met the eye. And then came Fritz Zwicky, and this is where the story truly begins to take shape. Fritz Zwicky was a Swiss-born astronomer working at the California Institute of Technology, better known as Caltech, in Pasadena, California. Zwicky was, by all accounts, a brilliant and extraordinarily creative scientist, but also a difficult and sometimes combative personality. He was known for insulting his colleagues, for making bold predictions that were decades ahead of their time, and for receiving very little credit for his insights during his lifetime. He was the kind of scientist who saw further than almost anyone around him, but whose manner made it easy for others to dismiss his ideas. In 1933, Zwicky was studying the Coma Cluster, an enormous collection of over 1,000 galaxies located approximately 320 million light-years from Earth. The Coma Cluster is one of the closest large galaxy clusters to us, and even with the telescopes of the 1930s, Zwicky could observe the motions of the galaxies within it by measuring the shifts in their light spectra, the way their light was stretched or compressed, depending on whether they were moving toward us or away from us. What Zwicky did was apply a principle from physics called the virial theorem. This theorem relates the average kinetic energy of the objects in a gravitationally bound system, in this case the galaxies in the cluster, to the total gravitational potential energy of the system. In simpler terms, it allowed Zwicky to estimate how much total mass the cluster needed to have in order to keep those galaxies gravitationally bound, to keep them from flying away from each other into the void of intergalactic space. When Zwicky compared the mass he calculated from the galaxy velocities to the mass he estimated from the visible light of the galaxies, the cluster's brightness, the result was shocking. The galaxies in the Coma Cluster were moving far too quickly. The visible matter, the stars and gas that Zwicky could see, produced nowhere near enough gravity to hold the cluster together. By his calculations, the cluster had roughly 400 times more mass than could be accounted for by the luminous matter. 400 times. The galaxies should have been streaming away from each other like sparks from a firework, dispersing into the emptiness of intergalactic space. But they were not. They were staying together, bound by an invisible gravitational embrace. Zwicky's conclusion was direct and bold. He proposed that the Coma Cluster must contain an enormous amount of invisible matter. Matter that could not be seen with any telescope, but whose gravitational influence was undeniable. He called this invisible substance Dunkel Materie, which is German for dark matter. It is important to note that Zwicky's original estimate of 400 times was too high, primarily because the value of the Hubble constant used at the time was inaccurate. Modern calculations with corrected values show a smaller but still enormous discrepancy. But the core insight, that most of the mass in galaxy clusters is invisible, was absolutely correct. And yet, despite the significance of this discovery, the scientific community largely ignored it. Zwicky's dark matter proposal was treated as a curiosity, a fringe idea from an eccentric scientist. Part of this was because the astronomical community of the 1930s simply did not have the tools or the additional evidence needed to confirm or deny the claim. Part of it was because Zwicky himself had a reputation for being difficult and for making grandiose claims. And part of it was simply human nature. The idea that most of the universe is invisible is a deeply uncomfortable one. It challenges our most basic assumption that we can trust our eyes, our instruments, our sense of what is real. It is much easier to assume that the observations are wrong, or that there is some simple explanation we are missing, than to accept that we are profoundly ignorant about the nature of reality. So the idea of dark matter sat largely untouched for decades. It flickered at the edges of astronomical discussions. A few other observations hinted at the same problem. In 1939, an American astronomer named Horace Babcock studied the rotation of the Andromeda galaxy, our nearest large galactic neighbor, and found that its outer regions were rotating much faster than expected, given the visible mass. But Babcock attributed this to light absorption, or unusual dynamics, not to unseen matter. In 1940, Jan Oort noted a similar anomaly in another galaxy. But again, these observations were seen as puzzles to be solved, not as evidence for a revolutionary new component of the universe. It was not until the 1970s that dark matter finally moved from the fringes to the center of astronomical thought. And the person most responsible for this transformation was a woman who had been told, repeatedly and explicitly, that she did not belong in science. Vera Rubin was born in 1928 in Philadelphia, Pennsylvania. From a young age, she was fascinated by the stars. She would lie in bed at night and watch the stars through her bedroom window, tracking their slow movement across the sky. When she told people she wanted to be an astronomer, she was discouraged at nearly every turn. When she applied to the graduate astronomy program at Princeton University, she was told that women were not admitted. This policy remained in place at Princeton until 1975. Undeterred, Rubin went to Cornell University and then to Georgetown University, where she earned her doctorate. Throughout the 1950s and 60s, Rubin faced the constant reality of being a woman in a field dominated by men. She was often the only woman at conferences, the only woman in the observatory, the only woman in the room. But she persisted. She was driven by a genuine, deep love of the cosmos, a curiosity that could not be extinguished by prejudice or indifference. In the late 1960s, Rubin and her collaborator Kent Ford began a project that would change the course of astronomy forever. They were studying the rotation of spiral galaxies, beginning with the great Andromeda galaxy. Using a remarkably sensitive new spectrograph that Ford had built, they measured the velocities of stars and gas at different distances from the center of each galaxy. The idea was straightforward. According to Newton's laws of gravity and Kepler's laws of planetary motion, the speed at which objects orbit a central mass depends on how much mass is enclosed within their orbit and how far they are from the center. In our own solar system, this is easy to see. Mercury, the closest planet to the Sun, orbits at a speed of about 47 kilometers per second. Earth, farther out, orbits at about 30 kilometers per second. Neptune, way out on the outskirts, crawls along at only about 5 kilometers per second. The further you are from the center of mass, the slower you orbit. This decrease in orbital speed with distance is called a Keplerian decline, and it is what you would expect in any system where most of the mass is concentrated at the center. Rubin and Ford expected to see the same pattern in spiral galaxies. The luminous mass of a spiral galaxy, the stars and gas, is heavily concentrated in the central bulge. So they expected stars on the outer edges of the galaxy to be orbiting more slowly than stars closer to the center, just as Neptune orbits more slowly than Mercury. But that is not what they found. Not at all. What they found was that the stars on the outer edges of the Andromeda Galaxy were orbiting just as fast as the stars near the center. The rotation curve, a graph of orbital velocity versus distance from the center, was flat, not declining, as Kepler's laws predicted for the visible mass. Flat, all the way out to the farthest distances they could measure. This was deeply, fundamentally wrong according to everything astronomers thought they knew. If only the visible matter existed, those outer stars did not have enough gravitational pull to keep them in their orbits at those speeds. They should have been flung outward into intergalactic space, like a ball released from a spinning string. The fact that they were not, the fact that they were orbiting so quickly and yet remaining bound to the galaxy, could mean only one thing. There was far more mass in the galaxy than could be seen. A vast, invisible halo of matter had to be surrounding the visible disk, extending far beyond the stars and gas, providing the additional gravitational pull needed to keep those outer stars in their orbits. Rubin and Ford studied galaxy after galaxy. They measured rotation curves for dozens of spiral galaxies, and the result was always the same. Every single galaxy they looked at had a flat rotation curve. Every single one. The pattern was universal. It was not a quirk of one galaxy or a handful of unusual cases. It was a fundamental property of all spiral galaxies. They were all embedded in enormous halos of invisible matter. This was the evidence that finally convinced the astronomical community. Vera Rubin's observations were so thorough, so consistent, so carefully done, that the existence of dark matter halos around galaxies could no longer be denied. What Fritz Zwicky had proposed 4 decades earlier, and been largely ignored for, was now established as one of the most important facts about the universe. Most of the mass in galaxies, and by extension, in the universe as a whole, is invisible. Think about that for a moment. A woman who was told she should not study the stars, who was turned away from a graduate program because of her gender, who faced skepticism and dismissal throughout her career, ended up making one of the most profound discoveries in the history of astronomy. She showed humanity that the universe is fundamentally different from what we thought it was. That most of reality is hidden. That the visible universe is just the tip of an enormous invisible iceberg. It is a story of persistence, of courage, of an unquenchable love of truth. And it is a story that I think deserves to be told slowly, and with deep respect. At the same time that Rubin was making her observations using visible light, radio astronomers were reaching the same conclusions using a completely different technique. Radio telescopes can detect the 21-centimeter emission line of neutral hydrogen gas, which extends much further out from the centers of galaxies than the visible stars do. This allowed radio astronomers to measure rotation curves at much greater distances from the galactic center. In 1972, Morton Roberts and Seth Shostak used the Owens Valley Interferometer to map the hydrogen rotation curves of 5 spiral galaxies. All 5 showed flat rotation curves, confirming Rubin's optical results. In 1975, Roberts and Whitehurst traced the rotation of the Andromeda Galaxy out to 30 kiloparsecs, about 100,000 light-years. Far beyond the optical measurements, the curve was flat the entire way. In 1978, Albert Bosma used the Westerbork Synthesis Radio Telescope to provide even more extensive confirmation for many more galaxies. By the late 1970s, the existence of dark matter halos around galaxies was widely accepted as real. It had gone from a fringe idea dismissed by most astronomers to one of the most important unsolved problems in all of science. And a new question had taken center stage. If dark matter is real, what is it made of? In 1978, a landmark theoretical paper by Gary Steigman and colleagues provided the first systematic framework for thinking about dark matter as a new kind of particle. They considered hypothetical particles that were massive, electrically neutral, and interacted only through the weak nuclear force and gravity. They calculated how many of these particles would have been produced in the hot, dense conditions of the early universe, and how their abundance would have changed as the universe expanded and cooled. What they found was remarkable. If such particles existed with masses and interaction strengths in the right range, the amount left over today would be almost exactly the right amount to explain dark matter. This coincidence became known as the WIMP miracle, where WIMP stands for Weakly Interacting Massive Particle. It suggested that dark matter might be made of heavy particles that interact only through gravity and the weak nuclear force. Particles that are all around us, but pass through ordinary matter like ghosts, leaving almost no trace. This framework became the dominant paradigm for dark matter research for the next several decades. Thousands of physicists and astronomers dedicated their careers to searching for WIMPs, building ever more sensitive detectors, designing ever more clever experiments, scanning the sky with ever more powerful telescopes. And while WIMPs have not yet been definitively found, the search for them has driven some of the most extraordinary experimental physics ever conducted. But we will come back to that later. For now, let us continue building our understanding of the evidence. Let me take you back to the night sky for a moment. Imagine you are looking at a distant galaxy, one that is billions of light years away. The light from that galaxy has traveled across the cosmos for billions of years to reach your eye or your telescope. Now imagine that between you and that distant galaxy, there is another galaxy, or a cluster of galaxies, sitting in the way. As the light from the distant galaxy passes near this massive foreground object, something extraordinary happens. The light bends. It curves around the intervening mass, like water flowing around a rock in a stream. This is not a metaphor. It is a direct physical prediction of Albert Einstein's general theory of relativity, published in 1915. Einstein showed that mass and energy curve the fabric of space-time itself, and that light follows these curves. When a massive object sits between us and a distant source of light, the massive object acts as a kind of cosmic lens, bending and magnifying the light from the background source. This phenomenon is called gravitational lensing, and it is one of the most beautiful and powerful tools in all of astronomy. Gravitational lensing comes in several forms. Strong lensing occurs when the foreground mass is very large and the alignment is close to perfect. In these cases, the background galaxy can be distorted into dramatic arcs, streaks, or even complete rings of light called Einstein rings. These Einstein rings are among the most visually stunning phenomena in the universe. Perfect circles of light formed by the gravitational bending of a distant galaxy's image around an intervening mass. They look almost artificial, as though someone drew a circle of light in space. But they are entirely natural, entirely predicted by the mathematics of general relativity. Weak lensing is a subtler effect. It occurs when many distant background galaxies are slightly distorted, not enough to create dramatic arcs, but enough to be detected statistically by measuring the shapes of thousands or millions of galaxies. By analyzing these subtle distortions, scientists can map the distribution of mass in the foreground, even if that mass is invisible. And this is the crucial point. Gravitational lensing does not care whether the lensing mass is visible or dark. It does not care whether the mass emits light or absorbs light or does anything with light at all. Gravity bends space-time regardless of the nature of the mass doing the bending. A kilogram of dark matter bends space-time just as much as a kilogram of ordinary matter. This means that gravitational lensing is a direct probe of dark matter. By studying how the light from distant galaxies is bent as it passes through galaxy clusters and large-scale structures, scientists can map the total mass distribution, including both visible and dark matter. And when they do this, the results are unambiguous. The total mass inferred from gravitational lensing is always far greater than the mass of the visible matter alone. There is roughly 5 to 6 times more mass than can be accounted for by stars, gas, and dust. The extra mass is dark matter. Scientists can even create maps of dark matter distribution across the sky. Large surveys, like the Kilo Degree Survey and the Dark Energy Survey, have used weak gravitational lensing to map the cosmic web of dark matter, revealing the vast filaments, sheets, and halos that form the gravitational scaffolding of the universe. These maps show a universe that is organized by invisible forces, a universe where the visible galaxies are like tiny bright ornaments hanging from an immense dark framework. And NASA's upcoming Nancy Grace Roman Space Telescope, named in honor of NASA's first chief astronomer and sometimes called the Mother of Hubble, will create the most detailed maps of dark matter distribution ever made. By observing billions of galaxies across a vast swath of the sky, the Roman Space Telescope will allow scientists to trace how dark matter is distributed and how it has evolved over cosmic history with unprecedented precision. But there is one observation related to gravitational lensing that stands out above all others as one of the most powerful and direct pieces of evidence for dark matter. It is the story of the bullet cluster, and it is, quite simply, one of the most remarkable observations in the history of astronomy. The bullet cluster, formerly known by the less poetic name 1E0657-56, is the result of a titanic collision between two massive galaxy clusters. This collision occurred approximately 3.8 billion light-years from Earth, and the resulting structure was first studied in detail in 2006 using two of the most powerful telescopes available: NASA's Chandra X-ray Observatory, which detects hot gas by its X-ray emissions, and the Hubble Space Telescope, combined with the Magellan Telescope, which was used to map the distribution of mass through gravitational lensing. Here is what makes the bullet cluster so extraordinary. When two galaxy clusters collide, the galaxies within each cluster are so spread out that they mostly pass through each other like two swarms of bees flying through one another. Galaxies are tiny compared to the vast distances between them, so direct galaxy-to-galaxy collisions are rare. But the hot gas in each cluster, the diffuse plasma that fills the space between galaxies, does collide. Gas interacts electromagnetically, which means the gas clouds from the two clusters slam into each other, slow down, heat up, and pile up near the center of the collision. This interaction is clearly visible in X-ray images from Chandra, where the hot gas appears as two large pink blobs near the center of the merged structure. Now here's the key. If there were no dark matter, if the only mass in the clusters were the visible gas and galaxies, then the gravitational lensing signal, which traces the total mass distribution, should be centered on the gas, because in galaxy clusters, the gas actually contains more mass than the stars in the galaxies. The gravitational center should be where the gas is. But that is not what the observations show. the gravitational lensing analysis revealed that the majority of the mass in the bullet cluster is not where the gas is. The mass is separated from the gas. It is located further out, in two distinct lobes on either side of the central gas cloud, coinciding approximately with the positions of the galaxies themselves. The mass passed right through, just like the galaxies did, while the gas was slowed down in the collision. This makes perfect sense if most of the mass is dark matter. Dark matter does not interact electromagnetically. It does not collide with gas, or with other dark matter, through any force other than gravity. So when the two clusters collided, the dark matter halos of each cluster passed right through each other, completely unimpeded, like two clouds of ghosts moving through one another. The gas, which does interact electromagnetically, got left behind in the middle, slowed and heated by the collision. The result is a system where the visible gas is in one place, and the invisible dark matter, revealed by gravitational lensing, is in a completely different place. This observation is often called the smoking gun of dark matter, because it is very, very difficult to explain with any alternative theory. Modified gravity theories, which attempt to explain the rotation curves of galaxies by changing the laws of gravity rather than postulating invisible matter, generally predict that the gravitational lensing should follow the visible matter. But in the bullet cluster, it does not. The gravity is where the dark matter should be, not where the gas is. This is exactly what you would expect if dark matter is real, and it is exactly what you would not expect if gravity were simply modified. Let me give you an analogy that might help you picture this. Imagine two large crowds of people running toward each other from opposite directions. When they meet, the people collide. They slow down. They pile up. They form a dense mass in the middle, bumping into each other, unable to pass through. Now imagine that each person in both crowds has an invisible ghost attached to them by a very long, very loose string. The ghosts are invisible, and they cannot touch or bump into anything physical. When the crowds collide, the people stop in the middle, but the ghosts keep going. They pass right through the pile of people, right through each other, and end up on the opposite side. If you then took a photograph that could somehow detect both the people and the ghosts, you would see the people clumped in the middle and the ghosts separated out on either side. That is essentially what the bullet cluster looks like. The gas is the people, the dark matter is the ghosts, and the gravitational lensing is the camera that reveals where the ghosts are. More recently, NASA's James Webb Space Telescope has observed the bullet cluster with even greater precision, refining the mass measurements and providing even more detailed data about the distribution of dark and visible matter. The bullet cluster remains one of the crown jewels of dark matter evidence, a single observation that speaks volumes about the nature of the universe. Now, let us go even further back in time. Not just back to the formation of galaxy clusters or the birth of individual galaxies. Let us go all the way back to a time when the universe was only 380,000 years old. This might sound like a long time, but in cosmic terms, it is the blink of an eye. The universe is currently about 13.8 billion years old. 380,000 years is to the age of the universe what the first day of a newborn's life is to the life of an 80-year-old person. We are talking about the universe in its infancy. At this incredibly early stage, the universe was a very different place. There were no stars, no galaxies, no planets, no moons, no asteroids, no comets. There was only a hot, dense, glowing fog of plasma, a soup of protons, electrons, and photons, all tangled together in a state of constant interaction. Photons, the particles of light, could not travel freely because they kept bumping into free electrons being scattered in random directions. The universe was opaque. If you could somehow have been there, you would have seen nothing but a blinding, uniform glow in every direction, like being inside a furnace. But as the universe expanded, it cooled. And at about 380,000 years after the Big Bang, the temperature dropped to roughly 3,000 degrees Kelvin, cool enough for protons and electrons to combine into neutral hydrogen atoms. This event is called recombination, even though it was actually the first time protons and electrons had ever combined. Once neutral atoms formed, the photons were suddenly free. There were no more free electrons to scatter them. The light was released, and it has been traveling through the universe ever since, stretching and cooling as the universe expanded. Today, those ancient photons, the very first light in the universe, fill all of space. They have been stretched by the expansion of the universe from their original visible and infrared wavelengths all the way into the microwave part of the electromagnetic spectrum. They form a faint, uniform glow that comes from every direction in the sky. This glow is called the cosmic microwave background, or CMB, and it is one of the most important observations in all of cosmology. It was discovered accidentally in 1965 by two radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, who initially thought the persistent microwave noise in their antenna was caused by pigeon droppings. The cosmic microwave background is remarkably uniform. Its temperature is about 2.725 degrees above absolute zero, and this temperature is almost exactly the same in every direction you look. Almost, but not quite. There are tiny temperature fluctuations, variations of only about 1 part in 100,000, that create a subtle pattern of slightly warmer and slightly cooler spots across the sky. These fluctuations are not random noise. They are the frozen imprint of sound waves that were rippling through the hot plasma of the early universe, acoustic oscillations driven by the interplay between gravity, which pulled matter together, and radiation pressure, which pushed it apart. Here is where dark matter comes in. These tiny fluctuations in the cosmic microwave background encode an extraordinary amount of information about the composition and structure of the early universe. Scientists can decompose the pattern of fluctuations into what is called an angular power spectrum, a mathematical description of how much variation there is at different angular scales. When you plot this power spectrum, it shows a series of peaks, called acoustic peaks, at regular intervals. The heights, positions, and spacing of these peaks depend on the exact composition of the universe, how much ordinary matter there is, how much dark matter, how much dark energy, and the overall geometry of space. Different compositions produce different patterns. By comparing the observed pattern with theoretical predictions, scientists can determine the composition of the universe with remarkable precision. The first acoustic peak was detected in 2000 by the Boomerang balloon experiment, which flew a sensitive microwave detector high above the Antarctic ice. Then came the WIMP satellite, which mapped the CMB from space between 2003 and 2012 with much greater precision. And finally, the European Space Agency's Planck satellite, which operated from 2009 to 2013 and produced the most detailed map of the cosmic microwave background ever made. The results from Planck were extraordinary. The pattern of acoustic peaks in the CMB matches the predictions of the Lambda CDM model, which is the current standard model of cosmology, with stunning accuracy. This model includes approximately 5% ordinary matter, 27% cold dark matter, and 68% dark energy. along with a cosmological constant, lambda, representing dark energy, and CDM standing for cold dark matter. What is particularly important is that the relative heights of the peaks are directly sensitive to the ratio of dark matter to ordinary matter. The odd-numbered peaks, the first, third, fifth, and so on, are enhanced by the gravity of dark matter, while the even-numbered peaks, the second, fourth, sixth, are not. This alternating pattern provides a very clear signature of dark matter in the CMB. If there were no dark matter, the peaks would look very different. They would be less pronounced, differently spaced, and the overall pattern would not match what we observe. This is not a marginal or ambiguous piece of evidence. The CMB measurements from Planck are among the most precise measurements in the history of science. The agreement between the data and the lambda CDM model with dark matter is so good that it leaves very little room for alternative explanations. Modified gravity theories like MOND, which can do a reasonable job of explaining galaxy rotation curves without dark matter, have great difficulty reproducing the detailed pattern of the CMB acoustic peaks. The cosmic microwave background is, in many ways, the most powerful and comprehensive evidence for dark matter that we have. And there is more. The CMB tells us not just that dark matter exists, but something about how it behaves. In the early universe, ordinary matter was tightly coupled to radiation, to the photons in the hot plasma. This coupling meant that any clumping of ordinary matter was quickly smoothed out by radiation pressure. Density fluctuations in ordinary matter could not grow, because every time gravity pulled matter together, radiation pressure pushed it apart again. Dark matter does not have this problem. Dark matter does not interact with radiation. It does not interact with photons. It is completely decoupled from the electromagnetic force. This means that dark matter density fluctuations could begin growing much earlier than ordinary matter fluctuations. While ordinary matter was being smoothed out by radiation, dark matter was already clumping together under its own gravity, forming the first gravitational wells, the first cosmic structures. After recombination, when the photons were finally released and the ordinary matter was decoupled from radiation, the ordinary matter fell into the gravitational wells that dark matter had already created. Dark matter acted as the scaffolding, the framework, upon which ordinary matter could accumulate and eventually form stars and galaxies. Without dark matter, the density fluctuations in ordinary matter alone would not have had enough time to grow into the structures we see today. There simply would not have been enough gravitational amplification between the era of recombination and the present day. The universe would be a smooth, featureless fog, with no galaxies, no stars, no planets, and no life. This is confirmed by computer simulations. The most ambitious and detailed cosmological simulations ever run, like the Millennium Simulation, the Illustris TNG project, and the Millennium TNG simulation, model the evolution of the universe from shortly after the Big Bang to the present day. They include dark matter, ordinary matter, gas physics, star formation, black hole feedback, and many other processes. When these simulations include cold dark matter, the resulting cosmic structure, the distribution of galaxies, galaxy clusters, filaments and voids, matches the real observed universe with remarkable fidelity. When dark matter is removed from the simulations, the universe looks completely different. Structures do not form. Galaxies do not appear. The cosmic web does not exist. And this brings us to one of the most awe-inspiring aspects of dark matter's role in the cosmos, the cosmic web itself. If you could somehow see all the dark matter in the universe, you would see an enormous, three-dimensional web of filaments and sheets stretching across hundreds of millions of light years, interconnected like the threads of an impossibly vast spider web. At the intersections of these filaments, where the dark matter is most concentrated, sit the great galaxy clusters, the most massive gravitationally bound structures in the universe. Along the filaments themselves, smaller galaxies are strung out like beads on a cosmic thread. And between the filaments, vast cosmic voids, regions that can span hundreds of millions of light years with almost no galaxies at all, fill the spaces like empty rooms in a cosmic house. This cosmic web is not a theoretical prediction. It has been observed. Large galaxy surveys like the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey have mapped the positions of millions of galaxies, revealing the filamentary structure of the universe in stunning detail. And gravitational lensing studies have directly mapped the dark matter within these filaments, confirming that the visible galaxies are indeed tracing the underlying dark matter framework. One particularly striking piece of evidence comes from observations of dark matter filaments using the Hubble Space Telescope. In 2012, astronomers used Hubble's gravitational lensing capabilities to study a dark matter filament connecting two galaxy clusters, mapping its three-dimensional structure for the first time. The filament was found to stretch for millions of light years, a bridge of invisible matter connecting two islands of galaxies across the void. Imagine the universe as a vast, dark ocean. The cosmic web of dark matter is like the currents in that ocean, invisible but powerful, shaping everything. The galaxies are like foam on the surface, carried along by the currents, accumulating where the currents converge, and sparse where the currents diverge. You can see the foam, but to understand why it gathers where it does, you need to understand the invisible currents below. There is another elegant piece of evidence we should talk about, one that comes from the study of how galaxies cluster together in space. In the early universe, before recombination, sound waves were rippling through the hot plasma of photons and ordinary matter. These sound waves created alternating regions of compression and rarefaction, like the sound waves in air that allow you to hear music or speech. When recombination occurred and the photons were released, these sound waves froze in place, leaving a characteristic pattern imprinted in the distribution of matter. This pattern is called baryon acoustic oscillations, or BAO. The sound waves traveled a specific distance before they froze, creating a preferred separation between over-dense regions of matter. This preferred distance, about 490 million light-years in today's expanded universe, acts as a kind of cosmic ruler, a standard length scale that scientists can use to measure the expansion of the universe and its composition. Baryon acoustic oscillations were first predicted theoretically in the 1990s and were first detected observationally in 2005 in two independent galaxy surveys. The pattern was clear. There is a subtle but measurable tendency for pairs of galaxies to be separated by this preferred distance compared to other distances. This finding matches the predictions of the Lambda CDM model with dark matter beautifully, and provides yet another independent confirmation that the standard cosmological model, with its 27% dark matter, is correct. More recently, the Dark Energy Spectroscopic Instrument, known as DESI, has been making the most detailed measurements of baryon acoustic oscillations ever. DESI is a remarkable instrument mounted on a 4-meter telescope at Kitt Peak National Observatory in Arizona. It can measure the spectra of 5,000 galaxies simultaneously, mapping the three-dimensional distribution of galaxies over enormous volumes of space. In 2025, DESI released results suggesting that dark energy might not be constant, that it might be evolving over time. This is a tantalizing hint that could change our understanding of the universe, though it is still preliminary and being carefully scrutinized. Let us pause here for a moment. Take another deep breath. Feel the weight of your body resting. Let your shoulders drop a little. You have been on a long journey already, traveling from the 1880s to the present, from the thoughts of Lord Kelvin to the observations of Planck and Desi. You have learned about galaxy rotation curves, gravitational lensing, the bullet cluster, the cosmic microwave background, structure formation, and baryon acoustic oscillations. Each of these is an independent line of evidence, each discovered through different methods, different instruments, different observations. And they all point to the same conclusion. Dark matter is real. It makes up about 27% of the universe, and it is the invisible architecture that holds everything together. But the question remains, what is dark matter? What is it actually made of? We know it is there. We know how much of it there is. We know where it is distributed. We know how it behaves on large scales. But we do not know what it is. This is one of the deepest and most tantalizing mysteries in all of science. And to explore it, we need to enter the realm of particle physics, where the candidates for dark matter live. The most popular and most extensively searched for candidate is the WIMP, the weakly interacting massive particle. As we discussed earlier, WIMPs are hypothetical particles that are heavy, with masses ranging from roughly 10 to 10,000 times the mass of a proton. They are electrically neutral, meaning they carry no electric charge, and they interact only through gravity and the weak nuclear force, one of the four fundamental forces of nature. The weak force is the force responsible for certain types of radioactive decay, like beta decay, and it operates over extremely short distances, shorter than the diameter of an atomic nucleus. The reason WIMPs have been so popular is the WIMP miracle we mentioned earlier. If you take a hypothetical particle with weak scale interactions and mass, and you calculate how many of these particles would have been produced in the hot, dense early universe, and then how many would have survived as the universe expanded and cooled, you get a number that is remarkably close to the amount of dark matter we observe. This coincidence suggested that dark matter might be intimately connected to the electroweak scale of particle physics, the same energy scale where the Higgs boson was discovered, and where the unification of the electromagnetic and weak forces occurs. WIMPs would be all around us, based on the estimated local dark matter density in our region of the Milky Way, approximately 0.3 giga-electron volts per cubic centimeter. Billions of dark matter particles could be passing through your body every single second. Every second. Right now, as you listen to this, as you lie still and quiet, an invisible river of dark matter is streaming through you, through the walls of your home, through the ground beneath you, through the entire earth, without touching a single atom. WIMPs are the ultimate ghosts, present everywhere, interacting with nothing, leaving no trace of their passage, or almost no trace. Physicists believe that very, very rarely, a WIMP might interact with an ordinary atom through the weak force. These interactions would be incredibly rare, perhaps a few per year in a detector containing a ton of material, and the energy transferred would be minuscule. But with sensitive enough detectors, in quiet enough environments, it might be possible to detect these faint whispers of the invisible. When two WIMPs encounter each other, they may annihilate, converting their mass into energy, producing pairs of ordinary particles, gamma rays, electron-positron pairs, neutrinos, and other particle-antiparticle pairs. This annihilation process is predicted by many WIMP models and forms the basis for indirect detection experiments. Telescopes and detectors that search for the products of dark matter annihilation rather than for dark matter particles themselves. The second major candidate is the axion. The axion has a completely different origin story from the WIMP. It was not originally proposed to solve the dark matter problem at all. Instead, it was proposed in 1977 by Roberto Pecce and Helen Quinn to solve a completely different puzzle in particle physics called the strong CP problem. Here is the strong CP problem in simplified terms. The strong nuclear force, which holds quarks together inside protons and neutrons, has a mathematical property that should allow a certain kind of symmetry violation called CP violation, where C stands for charge conjugation, the swapping of particles with their antiparticles, and P stands for parity, the mirror reversal of spatial coordinates. According to the mathematics of quantum chromodynamics, the theory of the strong force, CP violation should occur in strong interactions. But experiments have never detected it. The strong force appears to conserve CP symmetry to an extraordinary degree. This is the strong CP problem. Why does the strong force not violate CP symmetry when the mathematics says it should? Pecce and Quinn proposed an elegant solution, a new symmetry of nature that dynamically drives the CP violation to zero. The breaking of this symmetry gives rise to a new particle, which was later named the axion by Frank Wilczek after a brand of laundry detergent, because it cleaned up the strong CP problem. The axion is predicted to be extremely light, potentially trillions of times lighter than an electron. It is also very weakly interacting, even more ghostly than WIMPs. But if axions were produced in sufficient quantities in the early universe, they could collectively make up all of the dark matter. One of the most intriguing properties of axions is that in the presence of a strong magnetic field, they may convert into photons, particles of light. This conversion process works both ways. Photons can also convert into axions in a strong magnetic field. This photon-axion coupling, if it exists, provides a way to search for axions experimentally. The most prominent axion search experiment is ADMX, the Axion Dark Matter Experiment, located at the University of Washington. ADMX uses a powerful superconducting magnet and an extremely sensitive resonant cavity to search for the faint microwave photons that would be produced if axions in our galaxy's dark matter halo convert to photons inside the magnet. Other experiments, like Abracadabra, Mad Max, and various haloscope designs around the world, are also searching for axions using different techniques and targeting different mass ranges. In 2026, Fermilab announced a significant advance, a new electronically tunable quantum detector that can search broader frequency ranges for axion dark matter, significantly speeding up the search. The development of quantum sensing technology is revolutionizing axion detection, allowing scientists to probe previously inaccessible regions of axion parameter space. Part 2, the third candidate, is the sterile neutrino. We know that neutrinos exist. They are among the most abundant particles in the universe, produced in nuclear reactions in the Sun, in supernovae, in the Big Bang itself. There are 3 known types, or flavors, of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These neutrinos interact through the weak nuclear force, which is why they are so difficult to detect, passing through matter almost entirely unimpeded. A neutrino produced in the core of the Sun can pass through the entire Earth without interacting with a single atom. But physicists have theorized the existence of a 4th type of neutrino, called a sterile neutrino. That does not interact through any of the standard forces except gravity. A sterile neutrino would be even more ghostly than ordinary neutrinos. If sterile neutrinos have the right mass, in the kilo-electron-volt range, they could be warm dark matter, not as fast as hot dark matter, and not as slow as cold dark matter, but somewhere in between. Sterile neutrinos would be extremely difficult to detect, but they might reveal themselves through a slow decay process. When a sterile neutrino decays, it could produce an ordinary neutrino and an X-ray photon. If dark matter is made of sterile neutrinos, we might detect a faint line of X-ray emission at a specific energy from galaxy clusters or the Milky Way halo. In 2014, two independent groups reported the detection of a mysterious X-ray emission line at an energy of approximately 3.5 kilo-electron-volts from several galaxy clusters and from the Andromeda galaxy. This 3.5 kV line was initially suggested as a possible signature of sterile neutrino dark matter, and it generated enormous excitement. However, subsequent studies have produced mixed results. Some observations confirmed the line, others did not, and the interpretation remains controversial. It is still not clear whether the 3.5 kV line is a dark matter signal, an artifact of the data analysis, or a known astrophysical process that has been misidentified. The fourth candidate is primordial black holes. These are black holes that did not form from the collapse of stars, as most black holes in the universe did. Instead, they may have formed in the very first moments after the Big Bang, during the earliest fraction of a second, when the universe was incredibly hot, dense, and turbulent. If the density fluctuations in the early universe were large enough in certain regions, those regions could have collapsed directly into black holes. Primordial black holes could, in principle, have a wide range of masses, from far less than the mass of a star, all the way up to thousands of solar masses. Stephen Hawking, in the 1970s, was one of the first to propose that primordial black holes could be a significant component of the universe. And he also showed that very small black holes would slowly evaporate through a process now called Hawking radiation, the quantum mechanical emission of particles from a black hole's event horizon. Interest in primordial black holes as dark matter candidates surged after the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from merging black holes for the first time in 2015. Some of the black hole mergers detected by LIGO had unexpectedly large masses that were difficult to explain through standard stellar evolution. Some researchers suggested that these could be primordial black holes, potentially remnants from the early universe, that make up some or all of the dark matter. The idea that dark matter might be made of primordial black holes is still being actively investigated. Scientists use observations from gravitational lensing, the cosmic microwave background, and gamma-ray telescopes to constrain the possible mass ranges and abundances of primordial black holes. Current constraints rule out primordial black holes as the sole explanation for dark matter in most mass ranges. But some windows remain open, particularly for black holes with masses around the mass of an asteroid, or around tens of solar masses. Beyond these four main candidates, there are several more exotic possibilities that deserve mention. Fuzzy dark matter, also called ultralight dark matter or wave dark matter, proposes that dark matter is made of extremely light bosonic particles with masses as low as 10 to the minus 22 electron volts. These particles are so incredibly light that their quantum mechanical wavelength, their de Broglie wavelength, is on the scale of entire galaxies. Instead of behaving like individual particles, fuzzy dark matter would behave like a coherent wave, creating a smooth, wave-like distribution on small scales, while still behaving like cold dark matter on large scales. This wave-like behavior could help solve some of the small-scale challenges that conventional cold dark matter faces. In standard cold dark matter simulations, the centers of galaxies are predicted to have very high dark matter densities, forming steep cusps. But observations often show flatter, smoother cores. Fuzzy dark matter naturally produces these smoother cores because the quantum pressure of the wave prevents the dark matter from collapsing into extremely dense cusps. Similarly, fuzzy dark matter predicts fewer small satellite galaxies than standard cold dark matter, which might help explain why we observe fewer dwarf galaxies orbiting the Milky Way than simulations predict. Another exotic possibility is self-interacting dark matter, or SIDM. In the standard cold dark matter picture, dark matter particles interact with each other only through gravity. But what if they also interact through some unknown dark force? A force that acts only on dark matter and is completely invisible to ordinary matter and light. Self-interacting dark matter could scatter off itself, redistributing energy and momentum within dark matter halos. This could soften the dense cusps in galaxy centers and help resolve some of the small-scale tensions in the standard model. The concept of self-interacting dark matter leads naturally to one of the most fascinating and speculative ideas in modern physics: the dark sector. What if dark matter is not just one particle, but an entire family of particles, interacting through their own forces, forming their own structures, having their own complex physics, all completely invisible to us? There could be dark photons, dark electrons, dark atoms, maybe even dark stars and dark planets, an entire parallel universe of dark physics overlapping with our own, connected to us only through gravity. This is, at present, highly speculative. But it is not impossible, and some theoretical physicists take the idea seriously. The dark sector concept reminds us of just how little we truly know about the fundamental nature of reality. And then there are supersymmetric particles. Supersymmetry, often abbreviated as SUSY, is a theoretical framework in particle physics that proposes that every known particle has a heavier superpartner. If supersymmetry is real, the lightest supersymmetric particle, often called the neutralino, would be stable, electrically neutral, heavy, and weakly interacting, making it a perfect WIMP candidate for dark matter. For decades, supersymmetry was considered the leading theoretical extension of the standard model of particle physics, and the search for supersymmetric particles was one of the primary goals of the Large Hadron Collider at CERN. However, despite extensive searches at the highest energies ever achieved in a laboratory, no supersymmetric particles have been found. This has placed significant constraints on many SUSY models, though it has not completely ruled out supersymmetry. The superpartners might be heavier than the LHC can produce, or they might have different properties than the simplest SUSY models predict. The search continues. Let me now take you on a tour of the experiments that are actively searching for dark matter. These experiments represent some of the most extraordinary feats of engineering and ingenuity in the history of science, and they are being conducted in some of the most extreme environments on Earth and in space. There are three main strategies for detecting dark matter, and they are often described by analogy. Direct detection is like trying to catch a dark matter particle red-handed, detecting the tiny recoil when a dark matter particle bumps into an ordinary atom. Indirect detection is like following the breadcrumbs, looking for the products of dark matter annihilation or decay. Like gamma rays or neutrinos, that might be streaming toward us from regions of the universe where dark matter is concentrated. And collider production is like recreating the conditions of the early universe in a laboratory, smashing particles together at such high energies that dark matter particles might be created from the collision energy, just as they might have been created in the Big Bang. Let us start with direct detection. The basic idea is beautifully simple. Fill a large container with some target material, Put it deep underground to shield it from cosmic rays and other background radiation. Make it exquisitely sensitive to the tiniest deposits of energy. And then wait. Wait for a dark matter particle from the galaxy's halo to pass through the detector and, on the extremely rare occasion, bump into a nucleus of the target material. The reason these experiments must be deep underground is that cosmic rays, high-energy particles from space, constantly bombard the surface of the Earth. These cosmic rays would create far too many false signals in the detectors, overwhelming any faint dark matter signal. By going deep underground, beneath hundreds or thousands of meters of rock, the cosmic ray background is reduced by many orders of magnitude, creating the quiet environment needed to detect the faint whisper of a dark matter interaction. The most sensitive direct detection experiment in the world today is LUX Zeppelin, commonly known as ELS. LZ is located 4,850 feet underground in the Sanford Underground Research Facility in Lead, South Dakota. It is situated in a former gold mine, the Homestake Mine, which was also the site of the famous experiment by Ray Davis that first detected solar neutrinos and helped discover neutrino oscillations. LZ uses 10 tons of ultra-pure liquid xenon as its target material. Xenon is an ideal choice for several reasons. It is very dense, which increases the probability of a dark matter interaction. It is transparent to its own scintillation light, meaning that when a particle interacts with a xenon atom, the resulting flash of ultraviolet light can be detected. And xenon can be purified to extraordinary levels, removing radioactive contaminants that would produce unwanted background signals. When a dark matter particle interacts with a xenon nucleus, it produces a tiny flash of scintillation light, and also liberates a small number of electrons from the xenon atoms. These electrons drift upward through the liquid xenon under an electric field and are detected at the surface, producing a second signal. By measuring both signals, scientists can determine the energy and location of each interaction, and distinguish between the nuclear recoils expected from dark matter and the electron recoils produced by background radiation. In December of 2025, the ELS collaboration reported their latest results. While they did not find evidence for WIMP dark matter, they set the world's best limits on the strength of WIMP nucleus interactions, ruling out WIMP interaction cross-sections that were previously unexplored. This might sound like a negative result, but in dark matter physics, negative results are extremely valuable. Every time an experiment fails to find WIMPs in a previously untested region of parameter space, it narrows the range of possibilities, telling us where dark matter is not, and guiding future searches toward the remaining viable regions. LZ also made a significant positive discovery, the strongest evidence yet for coherent elastic neutrino nucleus scattering, or CEVNS, from boron-8 solar neutrinos interacting with xenon atoms. CEVNS is a process predicted by the Standard Model of Particle Physics in which a neutrino scatters coherently off an entire atomic nucleus, transferring a tiny amount of energy. This process was first observed in 2017 using a much smaller detector at the Spallation Neutron Source at Oak Ridge National Laboratory. But LZ's observation using solar neutrinos represents a major milestone. The detection of solar neutrino CEVNS in dark matter detectors is both a scientific achievement and a challenge. It is a challenge because these neutrino interactions look very similar to the dark matter interactions that the experiments are searching for. As detectors become more sensitive, they will eventually begin to see a background of neutrino events that cannot be distinguished from dark matter events on an event-by-event basis. This irreducible neutrino background, sometimes called the neutrino floor or neutrino fog, will set the ultimate sensitivity limit for direct detection experiments. Below this floor, new techniques will be needed to distinguish dark matter from neutrinos. Other major direct detection experiments include Exonaught, located deep beneath the Gran Sasso mountain in central Italy, which also uses liquid xenon technology and has produced some of the world's most stringent limits on dark matter interactions. Panda X, located in the Jinping Underground Laboratory in Sichuan, China, which is the deepest underground laboratory in the world, with 2,400 meters of rock overhead, providing the lowest cosmic ray background of any laboratory on Earth. And CREST, a European experiment that uses cryogenic detectors cooled to temperatures just above absolute zero, targeting very light dark matter particles with masses below 1 giga-electron volt, a regime where liquid xenon experiments are less sensitive. Now let us turn to indirect detection, the search for the products of dark matter annihilation or decay. The idea here is that if dark matter particles annihilate when they collide with each other, as WIMP models predict, then the densest concentrations of dark matter in the universe should be producing a steady stream of high-energy particles, gamma rays, neutrinos, positrons, antiprotons, and other antimatter particles. By searching for excesses of these particles above what is expected from known astrophysical sources, scientists might be able to identify the signature of dark matter. The most important instrument for indirect detection through gamma rays is NASA's Fermi Gamma Ray Space Telescope, which has been scanning the entire sky since 2008. Fermi's Large Area Telescope detects gamma rays with energies from about 20 million electron volts to more than 300 billion electron volts, covering the energy range where WIMP annihilation gamma rays are expected. Scientists have used Fermi data to search for dark matter signals from many different targets, the center of the Milky Way, where the dark matter density should be highest. Dwarf satellite galaxies orbiting the Milky Way, which are relatively simple systems dominated by dark matter with less confusing astrophysical backgrounds, galaxy clusters, and the diffuse gamma ray background across the entire sky. The center of the Milky Way has been a particularly active and controversial target. As early as 2009, researchers analyzing Fermi data noticed an excess of gamma rays near the galactic center that could not be easily explained by known astrophysical sources. This galactic center excess sparked enormous interest and debate, with some scientists interpreting it as a possible dark matter signal, and others attributing it to a population of millisecond pulsars, rapidly rotating neutron stars that emit gamma rays. In November of 2025, a new study by Professor Tomonori Totani of the University of Tokyo reinvigorated this debate. Totani performed a fresh analysis of 15 years of Fermi data and reported the detection of a hollow-like structure of gamma rays at an energy of approximately 20 giga-electron volts, emanating from the center of the Milky Way. The spatial distribution of this gamma ray emission, Totani argued, closely matches the shape expected from a dark matter halo. The energy spectrum of the emission matches models for the annihilation of WIMPs with masses roughly 500 times that of a proton. And the intensity of the signal is consistent with the expected annihilation rate within theoretical ranges. Totani was confident in his analysis. He said that if his interpretation is correct, it would mark the first time humanity has seen dark matter, and that dark matter would be a new particle not included in the current standard model of particle physics. This, he said, would represent a major development in astronomy and physics. However, the scientific community has responded with significant caution. Many researchers pointed out that the Fermi galactic center excess has been known and studied for over 15 years, and numerous analyses have failed to definitively connect it to dark matter. The galactic center is one of the most complex and messy regions of the sky, filled with pulsars, supernova remnants, molecular clouds, and many other gamma-ray sources. Disentangling a genuine dark matter signal from this astrophysical noise is extremely challenging. Stacy McGaugh, an astrophysicist at Case Western Reserve University, who is an expert in galaxy dynamics and dark matter, was among those expressing skepticism. He noted that the galactic center is a messy place with a lot of astrophysics, and that correctly accounting for all the non-dark matter sources, which constitute most of the gamma-ray emission, is essential for making a credible dark matter claim. He also pointed out a methodological concern. Totani appeared to use a dark matter density profile from simulations rather than from observational measurements. Real measurements suggest that the dark matter density near the galactic center may be lower than what simulations predict, which would weaken the expected dark matter signal and make the observed excess harder to attribute to dark matter. A critical test was also identified. If the gamma-ray signal truly originates from dark matter annihilation, the same signal should be detectable in dwarf satellite galaxies, which are simpler systems with less astrophysical noise. Dwarf galaxies are dominated by dark matter, with very little gas or stellar activity to confuse the signal. So far, the Fermi telescope has not detected a convincing dark matter signal from dwarf galaxies. As McGaugh noted, if the signal is dark matter, we should see it in dwarf galaxies too, but we do not. This suggests the galactic center signal may have an astrophysical origin. Jan Conrad, an astrophysicist at Stockholm University, echoed these concerns, noting that it is notoriously difficult to make dark matter claims with Fermi data. This is how science works, of course. Bold claims are made, scrutinized, tested, and either confirmed or refuted through independent verification. Totani's study may ultimately prove to be correct. It may be the first genuine detection of dark matter particles, or it may turn out to be another astrophysical mirage, a signal that looks like dark matter, but is actually produced by known physical processes in a very complex environment. Only time and more data will tell. But regardless of the outcome, the study demonstrates that we are tantalizingly close to the sensitivity needed to detect dark matter through indirect methods. Beyond gamma rays, other indirect detection methods are also being pursued. The alpha magnetic spectrometer, AMS-02, is a state-of-the-art particle physics detector mounted on the International Space Station. It has been collecting cosmic rays since 2011, searching for excess positrons, the antimatter counterparts of electrons, that could be produced by dark matter annihilation in the galaxy. AMS-02 has indeed detected an excess of positrons at energies above about 10 giga-electron-volts, which initially generated excitement as a possible dark matter signal. However, the excess can also be explained by nearby pulsars, and the dark matter interpretation remains uncertain. The IceCube Neutrino Observatory at the South Pole is another remarkable indirect detection experiment. IceCube consists of over 5,000 optical sensors buried deep in the Antarctic ice, instrumenting a full cubic kilometer of ice. When a high-energy neutrino interacts with an atom in the ice, it produces a shower of secondary particles that emit a faint blue light called Cherenkov radiation. IceCube detects these flashes of Cherenkov light and uses them to determine the energy and direction of the incoming neutrino. Dark matter particles trapped by the gravitational field of the Sun or Earth could annihilate in the cores of these bodies, producing high-energy neutrinos that IceCube could detect. So far, no dark matter signal has been found, but the experiment continues to improve its sensitivity. Looking to the future, the Cherenkov Telescope Array, or CTA. Currently under construction in Chile and the Canary Islands, will be the world's most powerful ground-based gamma-ray observatory. CTA will have far greater sensitivity than any previous gamma-ray telescope, allowing it to search for dark matter annihilation signals with unprecedented precision. It is expected to begin full operations in the coming years and could provide definitive evidence for or against WIMP dark matter. The third approach to finding dark matter is collider production, the attempt to create dark matter particles in a laboratory. The Large Hadron Collider at CERN, near Geneva, Switzerland, is the world's largest and most powerful particle accelerator. It accelerates protons to nearly the speed of light and then smashes them together, creating conditions that briefly mimic the extreme temperatures and energies of the very early universe. If dark matter particles have the right properties, particularly if they are connected to the electroweak scale of physics, they might be produced in these collisions. Dark matter particles, by their very nature, would not be detected directly by any of the LHC's detectors. They would escape invisibly, carrying energy and momentum with them. Scientists would detect their creation indirectly, by measuring all the visible particles produced in a collision and noting that some energy and momentum are missing. This missing transverse energy would be the fingerprint of an invisible particle. Despite extensive searches, the LHC has not found evidence for dark matter production. It has also not found evidence for supersymmetric particles, which were one of the leading theoretical motivations for WIMP dark matter. These null results have been disappointing for many physicists, but they have also been valuable, ruling out large swaths of parameter space and pushing theorists toward new ideas. The LHC is currently being upgraded to its high luminosity configuration, which will increase the collision rate by a factor of 10. This will allow much more data to be collected in the coming years, improving the sensitivity of dark matter searches. Proposals for future colliders, even larger and more powerful than the LHC, are also being discussed, though they would take decades to build. Another fascinating approach that has gained momentum in recent years involves the use of atom interferometers. These devices exploit the wave-like nature of atoms to detect extremely subtle changes in gravitational fields and accelerations. By watching how atoms interfere with each other as they travel along different paths, scientists can detect minute gravitational signals that might be produced by passing dark matter particles, or dark matter waves. Atom interferometer experiments are being developed at several institutions around the world, and some researchers believe they could eventually detect dark matter directly if it couples to gravity in certain ways. Now, let me take you on a small but important detour. We have been talking about the universe, about galaxies and clusters, and the cosmic microwave background. But I want to bring this story closer to home. I want to talk about dark matter in relation to you, to your body, to the hidden mysteries within your own biology. Right now, as you lie here listening to these words, dark matter is passing through you. Not metaphorically, literally, based on the estimated local dark matter density in our neighborhood of the Milky Way, which is about 0.3 giga-electron-volts per cubic centimeter. Billions of dark matter particles are streaming through your body every second. They enter from one side, pass through every cell, every organ, every bone, and exit the other side without interacting with a single atom. They do not touch you. They do not change you. They leave no trace. You are, at this very moment, immersed in an invisible ocean of dark matter, and you cannot feel a drop of it. This is one of the most extraordinary facts about our existence. We are not isolated from the dark matter that shapes the cosmos. It is everywhere, including right here, right now, in the room where you are. The total amount of dark matter within the orbit of Neptune in our solar system adds up to about the mass of a large asteroid, roughly 10 to the 17th kilograms. That might sound like a lot, but it is spread across an unimaginably vast volume of space, so the local density is extremely low. The dark matter in the space occupied by your body at this moment weighs less than a trillionth of a gram. It is there, but it is inconceivably dilute.